Hello.
Hello.
Huh. Hi. So I'm sorry. Last week I could not make up for the class.
Okay.
I was not well, and there was no way I could inform or anything. So
Okay. No problem.
yeah. Uh, so today I was thinking I'll do the questions from the previous assignment, last class assignment,
Okay.
and some more problems for dry etches.
All right.
Uh, okay. So we can start. I think um, people will
Okay.
join.
Okay.
Yeah. Just a minute. Yeah, so in week 9 we'll first start with a basic recap of etching. So in etching we have studied three types of etching, two types of etching, wet etch and dry etch. There is one more type called vapor phase etch. We um have not talked I think much about it, but yeah, so there is wet etch, in which basically we have etchants in the form of in liquid form, aqueous form, and um the byproducts are also in the liquid form, uh, basically soluble in the whatever solvent we have. In dry etching, we have etchants in gaseous form, and the byproducts are also gaseous. So this is usually done in vacuum chambers. Yeah. So, and then there is another etching technique called vapor phase etching. Vapor phase etching is basically uh, it's just like wet etch in the sense that we are sending chemicals. However, these chemicals are evaporated. So, they are in their vapor phase, and then they react with the films that we want to etch, and then the byproducts are again in the vapor phase. So, in some way it is like dry etching, but there is no plasma involved here. So, dry etching we usually call it when there is plasma involved and when it is done in vacuum chambers. Vapor phase etching, that is not the case. So, it is somewhere in between. Okay, so before understanding the different types of etching, we shall first look at different figure of merits for etching. So there are four main figure of merits. So first is etch rate. that is quite obvious. Etch rate is just nothing but the thickness of film that is etched upon unit time. Second is uniformity. So, uniformity means how uniformly we are etching throughout the die and from each die to die, and even from different wafers to wafer. So, uniformity can be affected by the variation in etch rate itself. It can also be affected by the film thickness. So, the deposited film stack itself might have some thickness variations. And there are a lot of other things like temperature or temperature uniformity, agitation, or we can like that can depend on many more things based on the process. Uh, so, uniformity, etch rate. Another thing is anisotropy. So, the cross section of our etching, that is also of interest to us. So, is it an anisotropic etch or an isotropic etch? So, basically isotropic etch means the amount of lateral edge. So, if this is my PR and this is the film. So, the etchant is coming from here. So, is it etching lateral vertically, or is it also going in the lateral direction, that is under the PR. So, that is determined by anisotropy. So, anisotropy is qualitatively described by the anisotropy coefficient or something, AF, that is 1 minus uh, rate of lateral edge upon rate of vertical edge. So, this thing will always remain between 0 and 1. So, if it is 0, that is it is completely isotropic, then we will have lateral edge is same as vertical edge. So, the undercut will look something like, so sorry, if this is my PR and this is the exposed part, then the amount that is being etched in the vertical direction will be the same as the amount that is being etched in the lateral direction. Sorry, just a minute. The undercut would look something like this. So, basically this distance will be the same as this distance. So, that is when AF is equal to 0, that is rate of lateral edge is equal to rate of vertical edge. When AF is equal to 1, that means we have a straight uh, etching. So, only the etching is done in the vertical direction and there is no lateral edge. So, that is anisotropy. Sorry, pen. Then there is selectivity. Selectivity basically tells how selective is our etchant to the photoresist, or how selective it is to the underlying layer. So, say I have silicon layer, uh, below this silicon layer I have SiO2 layer. So, I want to etch the silicon, but I want the etchings to stop once I reach the SiO2 layer. So, it should not etch the SiO2. Then I will say how selective is my etchant that I am putting from here. How selective it is towards silicon when compared to SiO2. So, the selectivity for A when compared to B is given by rate of etching of A upon rate of etching of B. So, in our case it will be rate of etching of silicon upon rate of etching of SiO2. So, those are the 4 basic figures of merit. Right. So, next in the case of wet etching, in general wet etching is like in most processes wet etching will be isotropic in nature. So, okay, but then we have also seen examples where it is anisotropic. However, in general, wet etching is like more like a diffusion phenomena of the etchants diffusing um, into the thin film, and so that gives a more isotropic nature compared to dry etching. So, first of all, what is wet etching? Wet etching is when fresh etchants we put these fresh etchants on top of our so basically we will just take our sample in a petri dish and put the etchants and agitate our sample or heat our sample. And then this etchant will diffuse through the stagnant layer towards our thin film, and it will start to etch the film. So, it will go on etching the film until it reaches the substrate. So, depending on how selective it is, it will etch uh, the etching will depend on how selective the etchants are. So, the basic phenomena is we first basic phenomena of wet etching is there are etchants that oxidize the film, and then these oxidized components form soluble complexes that dissolve off in the solution. So, so so basically all these reactions that you will see in wet etching can be like sorted out in some few simple reactions. One is oxidation, that will be the first step usually. Next is forming of soluble complexes. Yeah, so these two are the basic steps, and then they will depend on, since these are chemical reactions, they will depend on temperature, agitation, etc. And they will also depend on what kind of film we have. So, if we have a PCVD film or if we have a better quality like thermal oxide deposited, or uh, so based on the quality of the film also it will depend. Okay, so those are the basic things of wet etching, and we have also looked at some recipes. So, the first like one of the recipes that we saw is isotropic silicon etch recipe. So, in isotropic silicon etch, basically we again, like here we said there should be some oxidation step. So, first to oxidize silicon we have HNO3. Now, HNO3 will oxidize silicon to form SiO2, but now SiO2 is not a SiO2 is a solid, right? It is not a liquid. We need the byproducts to be in liquid state. So, we also add HF. So, HF will react with SiO2 to form uh, some soluble complex H2SiF6, and in addition to this we have acetic acid. So, it basically acts as a solvent. So, this recipe is called H for hydrofluoric acid, nitric acid HNA, A for acetic acid. So, HNA is a isotropic silicon etch recipe. So, as I said, HNO3 oxidizes, will cause silicon to go to SiO2, then HF will make SiO2 change into some complex H2SiF6, and CH3COH will basically act as a solvent, but it is also has a role that it reduces the ionization of nitric acid. So, if so this nitric acid mechanism is such that it should combine with HNO2 to form NO2 radicals. But if HNO3 keeps on ionizing, then there will be no HNO3 left to form NO2 radicals. So that is why we have CH3COH. It basically, in addition to being a solvent, it also helps in the reaction by limiting the ionization of HNO3. So that is the first recipe. So another important recipe that we have learned is, so it is very difficult to actually get anisotropic etching recipes in wet etch, but it is possible, and it is very highly researched in case of silicon. And some of the recipes that we have studied are, KOH etching. So KOH etching is basically just putting the sample in KOH and IPA, and then there is some temperature requirement also. So in KOH etching, this is an anisotropic etching, and this anisotropy arises primarily because of the fact that it etches different surfaces of silicon. So it etches 100 surface different from 110, and that is different from 111. So the etch rate is different for all these three surfaces, and because of that the anisotropy arises. So the etch rate anisotropy is somewhere around 400. So 100 it will readily etch, again 110 also it will readily etch, but 111 it will not etch, like the etch rate is very small for 111 compared to the other two surfaces. So that is KOH etching, and the only problem with this is it will form K plus and OH minus during the reaction. So these K plus are alkali, basically they are contaminants. So this process is not CMOS compatible. Because of that we do not want Na plus, K plus, all these ions are really easy to diffuse into different things. So we try to avoid this, and because of that we go to another anisotropic silicon etch recipe, TMAH. So TMAH is a compound, trimethyl ammonium hydroxide, I think. TMAH also has a similar etch rate. So this has 1 micron per minute. TMH also has 1 micrometer per minute. However, even though the etch rate is good, the anisotropy is not that great. It will the ratios are again high for 100 and 1, like 100 and 110, but you can see that there is a order of magnitude difference between this and this. So yeah, but however this does not produce any ions or alkali ions, so that is why this is preferred over KOH in certain cases, and this is CMOS compatible. So yeah, so then similarly we can also have recipes for other substrate, like SiO2 we have HF dip, like HF HS or buffered HF for SiO2, and there are many more recipes that were discussed in class. So yeah, so these were the important ones, so I decided to just, yeah. So let us do some problems on wet etching first. These are the previous assignment problems, then we will move on to dry etch. So the first problem is, yeah, this is quite simple. Etch rates of silicon, etch rates in silicon anisotropic etchant for different films are so much for silicon and SiO2 is so much. So, like 1100 nanometer per minute for silicon and 10 nanometer per minute for SiO2. If you use oxide as an etching mask to pattern silicon, what is the etching selectivity? Selectivity should be as high as possible. Okay, so they have already given the formula for selectivity here. So, selectivity just means that the ratio of etch rate of silicon to that of silicon dioxide. So, if it is high, that means that we can etch more of silicon without losing the entire mask here. So, when we are putting a etchant here, so it will etch the mask as well as the silicon. So, so the mask thickness will go on reducing and silicon thickness will also go on reducing, but we want only the silicon to reduce and the mask to stay there. So, that is why we need high selectivity, and to calculate selectivity they have already given the formula. So, it is pretty straightforward. S is rate of silicon, that is upon rate of SiO2, rate of etching of SiO2. So, it will give me 110. So, this is the correct answer. Okay. If the film has a plus or minus 3% thickness variation about the intended thickness and the etching rate has plus or minus 4% variation about the desired rate, so there is a variation in the film thickness and there is a variation in the etch rate. What is the variation in the etching time? Okay, so we basically have to find the maximum time that it takes to etch the film and the minimum time. So, when will it take maximum time? It will take maximum time for maximum thickness and for minimum etch rate. So, maximum thickness will be plus 3% basically, right. So, maximum thickness will be, say I had first a thickness of D, initial thickness is D, then we are saying plus 3% variation means maximum thickness D max is D plus 3% means 0.03 times D. So many nanometers say, okay, and so it will take maximum time when the rate is the slowest, right. So, the rate we will take it as R. So, R is the initial rate, I should not say initial rate, intended, or let me say mean thickness. Mean rate is R nanometers per minute. Okay. So, then this will be nothing but R minus, so we have to take the slowest possible rate 0.04 R, because 4% variation is there, nanometer per minute. So, this will so at this rate and for this much thickness I will take the maximum amount of time to etch my film. So, then T max will be nothing but D max upon minimum rate, R min, right. So, that will be nothing but I can take D common, 1 plus 0.03 upon R 1 minus 0.04, correct, minutes, like nanometer will cancel. Okay. So, now D by R is nothing but the time, expected time, right. So this is nothing. So from here I can get T max is equal to T expected time into 1 plus 0.03 is 1.03 upon, like you can do this, 0.96, and that will come out to be 1.07 T. So that I can write it as nothing but T of like 7% increase, right. So this I can write it as T of T plus 0.07 times T, right. So that is nothing but 7% increase. Similarly, you can also find out T min. T min will be nothing but the minimum thickness that it has to etch upon the maximum rate, and that also you will find out somewhere around 0.93 T. So that is minus 7%. So then plus or minus 7% is the correct option. Is that okay?
Yes.
Yeah, thank you. Okay, under what condition is surface reaction rate limited etching more probable? Okay, right. So they're asking, so first of all, what is surface reaction rate limited etching? So even in etching, just like in CVD, we have diffusion limited and surface reaction rate limited. So there are two processes. When we have a film and on top of the film there is a PR, and then there are etchants flowing by. So the etchant has to diffuse to the surface and then it has to react at the surface. So these two processes are there, and then the byproduct have to diffuse back. So surface reaction rate limited means the reaction is slow. It is able to diffuse to the surface, but then it is waiting to react here. So under what condition is this regime probable? That is, the reaction is slow and the diffusion is fast. At high temperature, do we expect the reaction to be slow? No, right? Dilute etchant, yeah, we expect reaction to be slow because the etchant is dilute, so reaction will take more time to proceed. Viscous and concentration etchant, no, then the reaction will be fast, and aggressive etchant, no. So dilute etchant is the answer. Which of the statements regarding the silicon dioxide etch using HF-BHF is correct? Okay. HF etches oxide by forming a soluble silicon fluoride complex in water. Yeah, so this is correct, right? HF etches silicon and silicon nitride faster than silicon dioxide. So this is not correct. In fact, it is not able to oxidize silicon, and that's why we use the uh, HNA method, like HF, nitric acid and acetic acid. So nitric acid is the one that oxidizes silicon, and then HF is used to remove SiO2. So this is definitely not correct. Oxide etch rate in HF reduces linearly with increasing temperature and HF concentration. So there is no reason why with increasing temperature the etch rate should reduce, right? So usually whenever we increase temperature and when we are increasing HF concentration, since HF is etching the oxide, so it will increase with increasing temperature. So this is not correct. High quality thermal oxide etches faster in HF solution than evaporation sputter PCVD deposited oxide. So again, this is not true. The high quality films usually take longer to etch compared to relatively lower quality films. So thermal oxide is at like a very high temperature process, thermal oxide deposition. So this is very like difficult to like it takes longer etch time for HF to etch high quality oxide films compared to lower quality like sputter or PCVD films. or evaporation. HF solution is not a safety hazard, so this is definitely not true. HF is like it's a very dangerous solution. So even though it's a weak acid, it is like it can penetrate skin and then damage tissues, and then it's like difficult to identify also because it's transparent and you don't feel the pain before. If it's very dilute, it's difficult to feel the pain when the exposure happens. It takes some time. So what? Okay. HF is silicon dioxide but not silicon. Intuitively, silicon can be etched by adding an oxidizing agent along with HF, which oxidizes silicon that can be etched by HF. Okay. So, it does not, it etches silicon dioxide but does not etch silicon. So, we can add some other oxidizing agent. So, that is what is done in HNA. Which of the statements regarding HNA etching of silicon is correct? NO2 necessary for the oxidation of silicon forms uh, unpolarized nitric acid H2O. Uh, okay, so NO2 is necessary for the oxidation of silicon. This forms from unpolarized nitric acid. Okay, so NO2 is formed when HNO2 reacts with HNO3, gives NO2 and some other byproducts. So H2 and water, H2O dielectric constant 80. Okay, they have given the result, is better compared to CH3COH in maintaining unpolarized nitric acid, hence improving the oxidation rate. So, this is not true because in general the solutions with lower dielectric constant uh, so the solutions with higher dielectric constant will be more polar. So, HNO2 is basically more readily splits into H plus and NO2 minus in H2O compared to CH3COH. So, this is not the correct option. Okay. Second, HNA etching of silicon is highly anisotropic. So, this is again not true because HNA is supposed to be isotropic. It has no selectivity towards uh, the different orientations of silicon crystal like 100 or anything. So, this is not true. In fact, that is why we use KOH. So, in KOH etching what happens is there is a passivation layer formed on 111 surface. So, because of that, so in this HNA we have a HF, right. So, HF will H111 even if it is passivated because HF will remove SiO2 on top of it. So, but in case of KOH there is no HF added to the solution. So, that is why whenever SiO2 is deposited on 111 surface, that will act as a passivation layer and that will reduce the H rate of the 111 surface. So, that is what is causing the uh, anisotropy in KOHs, but that cannot happen in HNA. That is why it is isotropic. So, this is wrong. Low HNO3 and high HF condition. Okay. So, then there is less oxidation and high HF means the SiO2 is getting removed easily. H rate is limited by surface oxidation. Yes, that is true. Free silicon surface in high HF concentration electrochemically develops micro roughness. Yeah, so that is true, right. So, HF even though we say that it does not etch silicon, it does create some roughness on the silicon surface, and that is because of the like different etching for different phases of silicon. So, so different orientation of the crystal will see different etch rates. Because of that, there will be some roughness on the surface. So, if there is some silicon exposed to HF, directly. So that will happen when there is HNO3 is low in concentration. So then that will cause surface roughness. This is true. Low HF and high HNO3 condition. H rate is limited by oxide removal. Oxide passivized silicon surface in high HNO3 concentration electrochemically develops micro roughness. So HNO3 is not actually etching silicon, so it should not develop any micro roughness even if more HNO3 is present. So yeah, it is limited by oxide removal, so there will be some oxide that will stay on the surface of silicon, but that won't cause micro roughness. So this is wrong. As we have seen before, the oxidation rate of 111 is greater than 100. If we use base like KOH or TMAH to etch silicon by forming soluble hydroxide complex, which plane will etch faster? Assume that these bases don't form soluble complex with oxide easily. So yeah, so they have already given us this hint. So these bases KOH and TMH don't form soluble complex with oxide. So if they are not forming soluble complex with oxide easily, so then they won't be able to form soluble hydroxide complexes. So we want an orientation that will not form oxide. So then that means 100 is the orientation that is less likely to form oxide compared to 111 because oxidation rate is lower. So then if you use base like this, which plane will etch faster? Could be 100 because it is less likely to form oxide, and since the oxide passivation layer won't be there, so KOH and TMH will easily etch it. Okay, a lot of metals are difficult to selectively etch and hence they can be patterned more easily by selective deposition using liftoff. Which of the following photoresist pattern is best suited for metal liftoff of narrow lines? So yeah, first of all, what is liftoff? So till now we were talking about patterning a film on top of a substrate and transferring this pattern to the underlying layer by etching. So we had PR and we had a substrate, and then we would either do wet etching or dry etching. So basically there will be etchants coming or diffusing to the surface and they will etch. But there is another process that is possible, uh, that is called liftoff. So in liftoff what we do is, instead of having a thin film beforehand, so here we had a substrate and a film, right. So we wanted to etch this film. So instead of doing that, what we can do is we can first have a substrate, and on top of the substrate I will first transfer the pattern from the from the mask to the photoresist. So that pattern is transferred now. Now I will deposit the film. So say I have to deposit gold film. So then I will sputter gold on top of this. So then that will form a, so then I will, this is gold. Now in this case the deposition is such that it is forming a like, okay, so this will be very difficult to lift off. So let me draw another. PR. Now when I deposit gold using sputter or evaporation, then the gold will come like this. Now what I will do is I will put this in a in solvents like acetone, IPA, and then I will wash off this PR. So when this PR gets washed off, so you know, right, this photoresist is basically it can be removed by acetone IPA and then a DI water rinse. So, we had learned this in the cleaning steps, cleaning lecture. So, or we even have specialized PR removers for that. So, by putting a PR remover or by putting acetone IPA, we can remove the PR. So, once the PR is removed, the gold on top of the PR will also be removed and we will get just gold at these place. Down there is substrate. So, instead of etching, now what we did is we lifted off the gold from the places where we did not want it. So, this is the lift off process, and to see that it is easy to see from this and this. If my acetone IP have to reach the PR to dissolve the PR, there has to be some wall open for acetone to go in, right. So, only then this PR will dissolve in the acetone and be removed. In this case it is not possible because the gold deposited everywhere, even on the side wall. So, so that is what they mean by ease of lift off. So, a lot of metals are difficult to selectively etch and hence they can be patterned more easily by selective deposition using lift off. Which of the following photoresist pattern is best suited for metal lift off of narrow lines? So, when they are saying photoresist pattern that is best suited, they are basically asking us where can I remove this PR more easily. So, in this case it is possible to remove the PR. So, we can send a dissolving solution through these paths, but then it depends on how much distance is there in between them. In this case it is not possible because the PR is not at all accessible. In the third case they have used a lift off resist. So, they have done a bilayer resist process. So, they have two resists with different development rates. So, this lift off resist has developed more compared to the top layer of photoresist. And so, now what has happened is in addition to this so in this case also if you see there is a space, right, but in addition to that, since LOR has higher development, so that has gone even more inside. So, because of that, even though I wanted the film to be deposited only here, but the LOR is even further away, and because of that this is the best way to actually go about it. So, here in the diagrams it is not very clearly visible, that is because they have shown it like this might not necessarily be that slanting, right. So, it is better to always have a second resist that has a that will develop even further. Process wise this is more reliable process. Is it okay?
Yeah.
Thank you. Okay. So, texturing the surface of the silicon substrate improves the light harvesting in single crystal silicon solar cells. Okay. From high throughput and cost effective cell perspective, which process is best suited for creating texture? Yeah. So, they have already told us like what they are looking for. They are looking for high throughput and they want cost effective process. So, and they want it the surface to be textured. So, the options are define the desired pattern using photolithography, one wafer after other, followed by HNA, that is isotropic etchant etching. So, batch will be individual wafers. So, what they are saying is we define each of these. So, uh, the texture we write it using some photoresist and then go on etching it. Or so this way has to be done one wafer at a time, and yeah. So, second method is to create 111 phased pyramids on the surface using an isotropic etchant bath, and then we can do as many wafers as we want in this bath. So, obviously this is better because we know that these anisotropic etchants they have selectivity towards 111. So, they will not etch the 111 phase because that will get passivated, and that is why it can be used for creating such not roughness exactly, but textured films. Contamination is typically low in surface reaction rate limited wet etching compared to diffusion rate limited etching. True or false? Okay. So yeah, so contamination can come from where? Contamination can come from the etchants, or contamination can be that the byproducts are not leaving. So, so in surface reaction rate limited wet etching, the diffusion is not a problem, surface reaction is a problem. So, diffusion is pretty fast. If diffusion is pretty fast, then the etchants, so then the byproducts can diffuse out pretty fast. So, this problem is solved. And also, since it is surface reaction rate limited, that means that the etchants are not very viscous, not so they are like dilute and mild etchants, and they can also diffuse in fast and diffuse out fast. So, then so that is the reason that typically contamination is low in surface reaction rate limited. So, this is true. Which of the following statements regarding wet etching is true? Anisotropy in wet etching is more likely in surface reaction rate limited regime. Anisotropy is more likely in diffusion rate limited regime. In KOH etching of silicon, this gets etched the fastest, and HF etches. Okay. So, this is definitely wrong. We know that HF etches SiO2 faster than anything else, like faster than silicon nitride and silicon. In KOH etching of silicon, silicon 111 gets etched the fastest. So, it is actually to the contrary, silicon 111 gets etched the slowest, because it will form a passivation layer of SiO2 on top of it. Anisotropy in wet etching is more likely in diffusion rate limited regime. So, any time in diffusion limited regimes, so if the reaction rate is not the thing, diffusion is a isotropic process. So, diffusion will happen equally likely in the lateral direction to the vertical direction. So, that is why in diffusion limited regimes, it is very difficult to get anisotropy. It will always be an isotropic etch. So, this is also wrong. Uh, so, then what is left is anisotropy is in wet etching is more likely in surface reaction rate limited regime. So, that is actually true. So, anisotropy usually arises in wet etching when we have selectivity towards different orientation. So, like in the case of silicon, silicon has 100 orientation and 111 orientation. So, 111 will not get etched, but 100 will get etched. So, because of that we are getting anisotropy. So, it is a reaction that is dictating the anisotropy, uh, not the diffusion. So, that is why this is true. So, it is more likely in surface reaction rate limited regime. It is like if I have a PR here and a PR here, and my say 100 plane is like this and 111 is something like this. So, 111, even though my etchants have reached 111, it will not etch 111. So, it is reaction rate limited, and when my etchants reach 100, it will etch it. So, that is why we are getting this anisotropy. So, it is reaction rate limited. Right. So, that was about wet etching. Uh, okay. So, do you have any doubts regarding the assignment questions? Anyone? Okay. If not, we will start with dry etching. Uh, so, I will explain the concepts as and when we see the problems. So yeah, before starting, some points I would like to mention about dry etching. Um, so when will you use wet etching and when will you use dry etching? That is the thing. So wet etching has more, it will give you a smoother like surface after the etching compared to dry etching. And so in cases when you want the lateral etch, so in MEMS, right, so we have devices like cantilevers. So say this is my silicon, so there is SiO2 below it and then there is silicon underneath. Okay, so say I want to make a cantilever with this silicon on top. So it's like, okay, so I want to make this structure hanging, so I want to remove this underlying SiO2. So like SiO2 will stay here but it will be removed from one side, so that will make this as a vibrating structure, right. So the silicon will be a vibrating structure, it will be anchored somewhere here to the underlying silicon. So I need to remove this central SiO2. So for that, if I just make a single opening, so say I am looking at it from the front view. So this is the silicon, this is middle, there is SiO2 and then lower there is one more substrate or whatever, it might be silicon, it might be something else, we do not mind. So this is the silicon that has to be hanging in the so it has to vibrate. So for it to vibrate, this SiO2 has to be removed, okay, and it has to be also removed in this direction. So it say we have to remove it till here. So to remove it inside, so we need a lateral edge, right, we do not just need a vertical edge. So in such situations, wet etch is a much better tool, uh, simply because dry etch we are using a plasma and that plasma will not give us a lateral edge unless like okay, how to say, okay. So in dry etch we get very good anisotropy simply because we are doing ion bombardments, or so this is my PR, and because there is an electric field that is there, because of the electric field these ions will come straight and bombard at the or rather react at the surface, and because of this ions, even though my free radicals, so reactive free radicals are there, they can go to the side walls or anywhere, but the ions will make sure that the reaction is most probable in the vertical direction, right. But then in cases where I do not want this, I will usually go for wet etch. So that is what I wanted to bring out here. And another thing is that uh, so there are so that was one advantage of the wet etch, but people usually prefer dry etching when we want vertical etch and for standardizing different procedures. So dry etching is more what to say, uh, it is more like you can make it automated, you can combine it with different processes more easily, and it is more reliable in terms of the yield. So the etch rates are more reliable, the contamination is less, so your device quality is more reliable, and you do not have to manually do anything, right. So you do not have to put your sample into chemicals, then dry it, clean it, so all that thing is done inside the vacuum chamber by the machine. So the automation in dry etch is one of the things that makes it very that makes it a very standard tool for etching. Uh, also, yeah, also you need less chemicals here because it's in the gaseous form, and it's easy to control like how much gases we want, and wastage is less. So that was about some comparison. There are many more points that are important, but yeah. So what is the basic requirement for an etching process? So for the case of dry etching, we need non-volatile products or volatile products. So yeah, so dry etching is basically, we have the etchants in the gaseous phase, and the byproducts are also in the gaseous stage. That's why it is dry, right? Because we don't want anything in the liquid state. The etchants will attack the surface, and some reaction will go on, and the byproducts of the reaction are some gases that will have the material in, like, yeah. So basically both etchants and byproducts are in the gaseous state, so this is volatile. In the provided options, which process does not require plasma? Okay. uh, so wafer cleaning, so wafer cleaning can be done with plasma or without plasma. So technically does not require plasma, but we can do it with plasma. So we can have oxygen plasma, and that can bombard on our wafer, and that will essentially oxidize all the impurities on the wafer, and we'll get a cleaner wafer. Physical vapor deposition. So physical vapor deposition requires plasma. In most PVD equipments, we'll have plasma, and yeah, that, so it depends on which type of physical vapor deposition you are talking, but generally sputtering and everything will have plasma. Dry etching, yeah, we have already talked about this. It has, we use plasma for dry etching. Spin coating does not require plasma. So wafer cleaning might require plasma. Spin coating definitely does not require plasma. So yeah, so fourth will be the answer. Spin coating is basically just putting the wafer on top of a chuck, and then putting our photoresist or whatever we want to spin coat on the wafer, and then as it spins, the photoresist will get coated on the wafer. So it's like a very physical process. What are the parameters that determine the minimum voltage of breakdown? Okay, so in a dry etch setup, we basically have two electrodes. Um, you can think of it like a elaborate capacitor, and then there is a gas in between, so say argon gas, and then this gas gets ionized to form plasma. So for any general plasma setup, there will be a breakdown voltage above which it will form plasma. So above which the argon gas will form Ar plus plus electron minus. So yeah, so basically the ionization of gas will happen after some minimum breakdown voltage. So what will this breakdown voltage depend on? Composition of gas, of course. Gap between the electrodes, yes, so it depends on the gap between the electrodes. So if there is smaller gap, we'll need lesser voltage. If there is larger gap, we'll have to ionize more argon gas that is in between. So it will depend on the gap between the electrodes. Temperature of the sample, so there is no question of sample here, right? It's just about the plasma. So this might not be the case. And pressure of the chamber, yes, of course. So pressure of the chamber will decide um, how many gas molecules are there in between the electrodes, and so it will decide the voltage required to ionize these gas molecules. So the correct answer is temperature of the sample. Yeah. So the plasma has nothing to do with the sample. So in a chamber, the mean free path of a molecule is, okay. So, yeah, mean free path is the path before which it collides with the next molecule. So proportional to pressure of gas. So if uh, proportional is not the correct word here, if the pressure of gas is higher, then that means that there are more molecules close to each other, then the mean free path before it collides the next molecule will be lower, right? So it is inversely proportional. Second option is proportional to gap between the electrodes. So so it technically should not depend on the electrodes, right? Because it's the mean free path, it will depend on the number of particles surrounding the okay, let us read the third option. Average distance between the collision of the molecules. So yeah, so this is the definition of mean free path. So this is the correct answer. Just a minute. Okay. Mean free path of the species in high pressure plasma etching is larger than low pressure plasma etching process. In high pressure we have so like just I said again, in high pressure plasma there will be more particles close to each other, so mean free path will be lesser. So this is false. Low pressure will usually have larger mean free paths. Okay, so in a high pressure plasma etching process, CF4 plus H2 plasma is used to etch silicon dioxide and silicon. Okay. Okay. So by adding more hydrogen, etch selectivity between SiO2 and Si is increased. Can you state the reason? Okay. So they are etching both silicon and oxide, but they are saying that if we add more hydrogen, right, more hydrogen, then selectivity between SiO2 and Si is increasing. So that means that maybe SiO2 is getting etched faster compared to silicon. Can you state the reason? It creates non-volatile passivation layer on SiO2. So, so it's very unlikely that hydrogen will form any kind of bonds with SiO2. So maybe not. Creates non-volatile passivation layer on silicon. So yeah, this is possible. So silicon hydrogen bonds are quite stable, right? So yeah, so it can form passivation layer on silicon, so that will lead to more etching of SiO2 compared to silicon. Creates non-volatile passivation layer on resist. But then why will that increase selectivity between SiO2 and Si? So this is definitely wrong. Creates more reactive species. So just by creating more reactive species, we won't be able to increase the selectivity. So this is also wrong. So yeah, among these two, this is correct, because creating a passivation layer on SiO2 by hydrogen is definitely not possible, right? Yeah. What is the average time between the collision of electrons with an average speed of 10 power 6 meter per second, and collisions typically happen every 0.01 meters? Yeah, this is trivial problem. They are asking the time between collisions. They have given the speed and they have told the distance is 0.01. So that will be nothing but 0.01 divided by 10 power 6, right, seconds. 10 power minus 8. Yeah, they have told the typical distance between which the collision will happen, and they have also given the speed. So we can easily calculate the time. High anisotropy is achieved with low ion energy and low ion flux. High ion energy and high ion flux. Low ion energy and high ion flux. High ion energy and low ion flux. Okay, so to achieve anisotropy, so in dry etching there are two different things, right? So one is what are the things that are reacting with the surface? So one thing is reactive neutrals. So they are not affected by ion energy or ion flux. So they are there all the time. So this is my PR. This is what is getting etched. Reactive neutrals will be there at the side walls, here, everywhere. Yeah. They are being affected by plasma in a way that the plasma might create these free radicals, but the energy and ion flux that they are talking about here is the ion flux that is bombarding the um, film. So, so if you have higher ion flux, so these reactive neutrals are not really directional, but the ion energy and ion flux are directional in nature. So if we have high ion energy in this direction, that will give us more number of ions will collide, or rather than number, yeah, ions will collide with the vertical surface, and that will give a more directional nature. Uh, so that will basically promote the reaction with the reactive neutrals. So we should definitely have high ion energy. Now the question is about ion flux. Should we have high ion flux or low ion flux? So can someone help me with this? I am confused. Low flux, is it? Yeah, so that is actually the correct answer, but so what is the reason behind it? Probably something like it might, um, if there are multiple ions, they might collide with each other and then collide to the side walls. Yeah, okay, yeah, yeah. Low flux to avoid collisions in lateral direction. Yeah, okay. Yeah, that makes sense, right? If we have multiple ions, then they might collide with each other and then hit the side walls. And because of that, the reaction will be promoted even at the side walls. So we don't want that. So, okay. Yeah, I think that is all I have for today. So, you have any doubts? So, I am not very good at chemistry, so I could not explain some things properly. But I tried my best. Thank you. Yeah. Okay. So, yeah, let's close the session for now. We'll meet in the next class. So, I think it's on process integration. That will probably be the last module. Thank you all.
Thank you.